Okay, so we're given that a car is going around a bank curved at a constant velocity, and we're given the radius. So essentially, I started by drawing a free body diagram where we have some angle theta that represents the angle that the curve is banked at. We have the normal force of the track on the car, and then we have the weight of the car, which is two-dimensional. Now, essentially, we're trying to solve for this angle theta, because if we look at this diagram right here, we can use some simple trigonometry to understand that this angle of the banked curve and the angle between the vertical and this little string will actually be the same, in the same way that this angle is related to the weight here. This angle is also related in the same way. So if we're able to solve for this angle, we can solve for this angle that we are actually solving for in the problem. And we're able to solve for this angle by using Newton's second law for the centripetal force and centripetal acceleration. We're also able to make some substitutions so that we are not required to find the mass. And once we're in this situation where we have all of the variables that are needed, we can plug in our numbers and find that this angle of the banked curve is equal to 24 degrees, which is equal to the angle between the string and the vertical while it is curving around, or going around the curve. Okay, so next problem. So we have 3 blocks, and we want to find which one has the most energy dissipated by non-conservative forces, or friction in this case. So we can use the conservation of momentum with conservation of mechanical energy rather with non-conservative forces to see in which case the work of the non-conservative force will be greatest. And in the case that the work of the non-conservative force is greatest, then that means that more energy is going to be dissipated by the friction. So in this case, we have no potential energy. All of the energy of the block is essentially kinetic because it doesn't really change height. So we could see that the work of the non-conservative force is solely based on the initial velocity, which is a constant between all 3 blocks, and its mass. We also know that it's negative, which means the work is taking energy from the system, which is what we'd expect. This also tells us that the most negative work done is going to be the one that takes the most energy from the system. Now if we look at this example here where the block is moving upward, we know that the block is going to come to rest at some point up here and then start falling down, but we're just concerned where it first comes to rest. So if we use the same equation that we used up here, we have the conservation of mechanical energy with non-conservative forces. If we manipulate that a little bit, then we can see that the work of the non-conservative force is essentially based on the final potential energy, minus the initial potential energy, minus the final kinetic energy. Now it's important to note that these two are exactly the same because the initial velocities are the same between all the blocks. And remember, we want the most negative answer, but in this case, our final height is actually going to be higher than our initial height, which means our final potential energy is going to be greater than our initial potential energy. So if we plug in a dummy number, for example, we'd get 3 minus 2 minus the 1/2 mv squared, and we can see that this number is actually going to be greater than this number, which means that we know in situation 2 there's less less energy dissipated by the non-conservative forces. So we can say that scenario 2, scenario 1. Now let's look at the last scenario where the block is moving downwards. We use the same equation, and after some manipulation, we can see that the work of the non-conservative force is based on the same thing as in the previous example, but because the final height of the block is going to be much smaller than the initial height of the block, we can see that because this number is going to be, smaller than this number, that this is going to be some negative number minus this constant that we were looking at. Once again, this is the initial kinetic energy. This is constant between all the three blocks because the initial velocity is the same between all three. So it's going to be some negative number minus some negative number, which is going to be the most negative of them all. So we can say that 2 has the least amount of mechanical energy dissipated by friction, 1 has slightly more, and 3 has the most. So if we look to our final problem, the loop-to-loop, we're trying to find the velocity that is required by this block in order to have it round the curve. So I started by drawing a free body diagram of the block. We can see that there's the weight of the block and there's the normal force of the track on the block. Now, because we're trying to find the velocity, we can use Newton's second law and plug in for centripetal acceleration and whatnot. We know that the centripetal net force is equal to these two forces that are pointing inwards. And then we can manipulate this equation here to eliminate our unknowns. For example, it's rather difficult for us to know the normal force. So if we analyze this force, if we assume that the block falls off at this moment, so the block comes up and then falls, then we can assume that normal force is 0 because there's no contact between the track and the block. And when we do that and we solve out for velocity, that will actually give us the minimum velocity that's needed to not fall on the track and make it all the way through. And when we solve, we find that the velocity is equal to 3.83 meters per second.